So example 22 here, we're given the function 2x squared minus 3 over x squared minus 4, and we're asked these questions. What is the domain of f of x? Okay, well, when I look at this, my domain convention, it's a rational function, so I have that fraction bar and I have a variable on the bottom, so can I get zeros on the bottom? So what I'm going to look to do is see, okay, well, can I figure it out if that's going to be the case? The bottom does factor into x plus 2 and x minus 2, which makes it a little easier for me to determine whether or not that can happen, because if any part of that product becomes 0, the whole product becomes 0. So a negative 2 would make x plus 2 0, making the whole thing equal to 0, or x being 2 would make x minus 2 equal to 0, making the whole thing 0. So 2 and negative 2 are my domain restrictions. Please make sure you differentiate between domain restriction and domain. A domain mentions what the values of x are, not what they aren't. Yes, I could say x is not equal to 2 and x is not equal to negative 2. That's not a domain. Those are restrictions. Ultimately, my domain is negative infinity to negative 2, then from negative 2 to 2, then from 2 to infinity. If I wanted to read it more in English, I would say all real numbers except 2 and negative 2. That's where students get confused about a domain. You know, they think that just mentioning the restrictions is a domain. No, you're just mentioning the things it isn't. Tell me what it is. Well, it's everything else but those. Add that little tidbit to it and you're good. Find all values of x such that f of x equals 5. Well, that means that we're going to set this equation 2x squared minus 3 over 5x, or over x squared minus 4 equal to 5. I'm going to solve it as usual, because what I have here is I have two x's involved here, but they're both the same exponent. So I could use basic equation solving techniques to solve this. I don't have to use any quadratic formulas or anything like that. So I multiply both sides by x squared minus 4 to get 2x squared minus 3 equals 5x squared minus 20. That if I start moving things, so I get all my x squareds on one side and all my constants on the other, I subtract 5x squared from both sides. I add 3 to both sides. I end up with negative 3x squared equaling a negative 17. I divide both sides by negative 3 to get that x squared equals 17 thirds. And then I would square root both sides, putting a plus or minus symbol in there. So x would equal plus or minus the square root of 17 over 3. Now, for me, that's an acceptable answer, but for some textbooks, and if you're looking at an answer key, if you're looking up an answer that you may have got it online or something, they may not present it that way because of the fact that even if I'm writing the square root of a fraction, that means that the denominator is ultimately being square rooted. We do not like having irrational numbers in a denominator. The whole premise behind it is, we don't care so much about it anymore, but the whole premise behind it is, when you're dividing something, you're trying to figure out how many equal parts you're going to divide it into. Well, if I'm trying to divide by an irrational number, I basically say I'm trying to divide it into a number of parts that I can't even really define. So that's why they don't want it down there. So what they would do with this is multiply the top and bottom by the square root of 3. That would square the square root on the bottom essentially. And therefore I could write this as the square root of 51 over 3 plus or minus. So that's the way that they might write the answer more often than not for a situation like this, because it's rationalized. I'll let you know a hint right now. WebWork doesn't care. Okay, much like I don't really care. I just give you this information because when you're comparing answers, if you're doing a problem from the textbook that might be asking you to do something similar to this, they're always going to rationalize the denominator. So find any values of x such that f of x equals 0. So here, now I could do two different things that are looking from two different standpoints. If I'm looking to see where f of x equals 0, then really only what's going to happen is that the numerator would have to equal 0. Okay? Because 0 over a number is 0. But the reason why I could say that is if I set it equal to 0 and multiply both sides by the denominator like I did in the previous problem, except 5 was there, well, I'm multiplying 0 times x squared minus 4. I get nothing. I get 0. So it comes down to the point where 2x squared minus 3, the numerator, is going to have to equal 0 for that to happen. I solve that. I get x equals plus or minus the square root of 3 halves. Again, you might see some rationalization of the denominator for that, because that, again, some textbooks are big against this. or they might just turn that to a 1.5 instead and say, well, I can take the square root of a negative of a decimal. I'm fine with that. Just just not a denominator of a fraction. So you might see any one of these. I mean, the square root of plus or minus the square root of 3 halves, plus or minus the square root of 1.5, plus or minus the square root of 6 over 2. All the same thing. All the same thing. What is the range of f of x? Well, the range of f of x could ultimately be affected by any horizontal asymptotes. Because remember, a horizontal asymptote essentially is in the form y equals a number, which means that's a number that my function is going to try to avoid for a y value. Doesn't mean it's actually going to avoid it, but I'm looking to see, is there going to be some sort of range restriction on this? Again, exploring ranges gets to be a little tricky. You have to know something about the graph, but there is a horizontal asymptote at y equals 2. Further investigation, which means looking at a graph, you would see that f of x avoids that horizontal asymptote every single time it gets anywhere near it. And this knowledge of f of x not actually ever equaling 2 can be established algebraically, but you can establish it much more quickly and other things about this graph looking at the graph itself. And that becomes important because even if you do have a horizontal asymptote or oblique asymptote, it doesn't mean that the graph is never going to pass through that asymptote. It's an end behavior. At the very ends of the graph, as your x goes to infinity or as your x goes to negative infinity, it will start behaving that way. But there are some graphs that could actually pass through the asymptotes towards the center of the graph, where most of your vertical asymptotes would tend to lie. So looking at a graph becomes more and more necessary the more and more complicated the polynomials in the numerator and denominator are, and that usually means higher degree. So the higher degree that they are in the numerator and denominator, the more varied the behaviors can be for these rational functions. So if you look at a graph of this more carefully, again, you can see that it is avoiding y equals 2 completely. It looks like it actually is going along it at some point, but that's getting infinitely close. If you keep zooming in, you would see that there's always going to be a space between y equals 2 and the graph itself. But you also see right here at this point here, it seems like in the center portion, that's the highest it reaches is 3/4. And that means that you have basically a gap of y values between 3/4, including the 3/4, and y equaling 2, where y can't equal. So anything that's more than 3/4 and all the way up to 2 is not part of the range. So the range has to be defined more carefully because it's excluding all values that are more than 3/4 and all the way up to 2. So the range would be better defined as stating that it goes from negative infinity to 3/4 and then from 2 to infinity, including the 3/4, excluding the 2.